Hi everyone, my name is Karan, and today I'm excited to present our work on running distributed systems like Clockwork. This is joint work with my co-authors at Penn, Robbie Gifford, Andy Liu, Andres Heberlin, and Lin Fan. Let's imagine a scenario where there's some clients, say Alice and Bob, who want to use a complex critical service such as a banking application. This service is deployed in a data center. But if there were only one machine, the service would be down as soon as that machine fails, which could happen due to hardware faults, software issues, or misconfigurations. So the functionality of the service needs to be replicated. State machine replication, or SMR for short, is a standard technique to achieve replication. SMR is implemented using multiple servers for redundancy. Each server stores a copy of the state machine, which is deterministic and has the same initial state for all replicas. So even if some servers fail, the clients can send requests to the servers which are still alive. Therefore, the service as a whole will then remain available as long as not too many of the machines fail. There is an entire area of research dedicated to designing protocols for SMR. In the past 3 decades, there's been a lot of great work on SMR protocols, and there are dozens of solutions available for all sorts of different scenarios. But still, these protocols are not as fast to achieve as we would all like. They have to do a lot of coordination, which adds a significant overhead in terms of the throughput and tail latency, and they need a lot of machines to essentially do the work of one due to some impossibility results such as the FLP theorem. So we wanted to see whether this is truly inherent or whether there is something we can still do to improve things further. In our paper, we showed that the fundamental reason behind these SMR protocols having to do a lot of hard work is the underlying key assumption about the system model. In particular, these protocols assume the asynchronous model, which is very conservative. People want to build systems that are robust, and the asynchronous model results in a system that can work correctly under very difficult conditions. But as you can see here, the clocks on the tree nodes are completely out of sync, packets are getting dropped and delayed, and this results in complete chaos. The key question is whether the asynchronous model is a good fit for modern data centers, where clocks are excellent, network data is bounded, physical layer packet corruptions almost never happen, the entire network topology is known, and we can know and control the entire workload too. Basically, we are trying to make systems robust by assuming a very challenging environment. But at least in single-tenant data centers, we do have a lot of control about both the workload and the hardware. And therefore, we should be able to ensure that the bad conditions do not happen. Let's see if we can use an alternative model instead of the asynchronous model, which is extremely pessimistic since it assumes the worst for the network. One possibility is the fully synchronous model. But the issue now is that the model is overly optimistic since it does not capture the limitations of real-world hardware. The system is in perfect harmony here, since there's no packet loss at all, and the clocks on all the nodes are perfectly synchronized. But in a real world, physical layer packet corruption can still happen, even if rarely, and clocks will not be perfectly synchronized. Can we make a model which can bridge the gap between the conservative assumptions used by the asynchronous model and the idealistic assumptions used in a fully synchronous model? There is a spectrum here, and neither of the two traditional models is in the right spot for modern single-tenant data centers. The asynchronous model, as shown on the left, is too pessimistic, and the fully synchronous model shown on the right is too optimistic. The key question here is whether we could design a model that is in the middle, a model which is closer to what the systems actually encounter. So we propose the quasi-synchronous model. Firstly, for clocks, we will assume that they're synchronized up to some known amount phi. This could be achieved by buying really good clocks, such as modern oven-controlled crystal oscillators, and or by using state-of-the-art clock sync systems such as Firefly. Now, we don't want to just assume away packet drops altogether. Instead, we will assume no more than k physical layer losses such as corruptions. We'll do something else to get rid of few drops, and I'll talk about that in a moment. But given that Ethernet links are supposed to corrupt packets at a rate of at most 1 in 100 million, the odds of encountering more than, say, 3 corruptions in a row are so low that it no longer makes sense to design systems for that rare case. In our model, At least one of the k plus 1 consecutive transmissions sent in a row will be received after some time delta. Let's see how we can actually achieve that upper bound delta. Imagine two nodes A and B sending packets over the same link. In the asynchronous model as shown here, they might send the packets at the same time. So there's a lot of queuing in this case, and some packets are going to get dropped due to the lack of coordination. In the fully synchronous model, we assume a bound, but the bound cannot be achieved because there's too much data, and the packets just cannot get to the other end in time. This happens because this model does not take the limitations of real-world networking hardware into account. Now, in our quasi-synchronous model, we promise a delay bound that depends on the amount of data that is to be sent and the available link capacity. This bound is higher than it would be if only one node were sending packets. The nodes here can coordinate using the synchronized clocks to make sure that the packets they're sending do not collide in the queue, and then no more than a negligible amount of queuing happens. We can reason about the amount of queuing using the clock sync bounds. If you're given enough information about the network, control over the workload, it's possible then to get a hard bound on queuing, and thus avoid queue drops and any non-trivial delays. Therefore, delays are bounded and queue drops will not happen, and we only have to deal with the physical layer corruptions, which are extremely rare. Now, there's a few more assumptions that we need to consider in our model, but not too many, and the full details are in our paper. Overall, our model doesn't just assume some upper bound delta on the message delivery time. It assumes that the system actually has the means to guarantee such an upper bound delta. So far, I've talked about the motivation for our work and the quasi-synchronous model. I will now describe the main high-level ideas of Watchmaker, an SMR protocol we developed for the quasi-synchronous model. This is the model we use for Watchmaker specifically, and in the interest of incremental deployability, we wanted to assume quasi-synchrony only for the replicas, which is sufficient. Our algorithm gets full control of the quasi-synchronous replica network. To get the clock synchronized, we use a clock network. Importantly, this clock network is used for correctness in our case, as opposed to for just optimization as in prior work. Before I dive deep into the Watchmaker protocol, let me remind you that there are two key safety properties for SMR, agreement and ordering. To maintain agreement, each alive replica must receive every client request. And for ordering, each alive replica must process the request in the same relative order. The key reason that makes it difficult to provide the safety properties in the asynchronous model is that the network can be unreliable. For example, consider a setting with two replicas and two clients. When Alice sends a request to both the replicas, it's possible that one of her replicas packets got dropped, but not the other. This would violate the agreement property. Additionally, if both Alice and Bob send requests at roughly the same time, it's possible that the requests arrive in different orders. This would violate the ordering property unless this issue is fixed. We will now discuss the watchmaker algorithm. I had mentioned earlier that the quasi-synchronous model enables us to prevent queuing delays within a replica network through careful coordination among the replicas. In Watchmaker, when a client has a request, it sends it to one of the replicas. And when a replica gets a request from a client, it'll then send it to all the other replicas. So basically, the replicas have to constantly broadcast data to each other. We can simply divide up the time into little slots, as you can see here in the illustration. Each replica gets to send in some of the slots, while all the other replicas remain silent in those slots. For Watchmaker, we'll use a simple round-robin network schedule. This ensures the agreement property, at least in the case where there's no failures. For the ordering property, whenever a replica sends a packet of the replica network, it'll also include the number of the time slot it is using. You can see that in this illustration. In a failure-free scenario, the replicas could basically just order everything by the timestamps. But we also need to take packet loss into account. So each replica will include the number of the highest slot such that it has received the contiguous sequence of all the packets up to that slot without gaps. We'll call this number the high watermark, or H for short. Replicas don't execute a request until they know that all the other replicas got in. So they'll only execute requests once they're covered by the high watermarks of all the alive replicas. Now, this would be a very horrible idea in an asynchronous network where packet losses can happen quite a bit. And if we trigger a recovery action each time this happens, that would be extremely disruptive. But for our quasi-synchronous model, we have taken care of all the queue drops, and the system runs essentially like clockwork. So all that we are left with are the incredibly rare physical layer packet losses. Doing recovery in this case, when a physical layer packet corruption happens once in a blue moon, seems fine. Let's see how to actually recover when a physical layer drop occurs. If the packet got dropped, the high watermark will stop increasing, as shown here for replica 1. When this happens, the other replicas can tell that a loss happened and which packet was lost using the high watermark. Then some other replica can just retransmit the lost request. Here, we will use our bounded packet loss assumption. Since packet losses are extremely rare, so is recovery. In this case, replica 2 will send k plus 1 copies of the retransmission to ensure that at least one copy reaches replica 1. So I've talked about the failure-free scenario and how to handle packet losses. But there's a few other things that we need to consider. For instance, how can we recover if a replica fails? I'm not going to go into the details here, but I encourage you to read our paper if you're interested in learning more about the overall algorithm. Here I'm showing you the full watchmaker algorithm on this slide, not because I want you to read it now, but just to briefly tell you that we have to do some bookkeeping to handle the additional issues, and you have to be a bit careful in certain cases. But fundamentally, the algorithm is not that complicated. It basically does what we just sketched on the earlier slides. Now that I've shown you the watchmaker protocol, let's have a look at the evaluation to see how well watchmaker works in practice. The full evaluation of watchmaker is in our paper, but for the purposes of this talk, I'll focus on the throughput and latency aspects of watchmaker. Let's have a look at the throughput first. So usually people measure this by making a really simple state machine, say one that only echoes its inputs back to the sender. This makes sense because if the state machine itself is slow, then of course the throughput will be low too. But then this is not the SMR protocol's fault. So we set up an experiment with an echo state machine and we evaluated both open loop and closed loop workloads. We compared the throughput of watchmaker to a number of existing protocols, such as Measure and NoPaxos. If you haven't heard of these, all that you need to know is that these are state-of-the-art protocols. In both these graphs, you will see that as we increase the throughput, each protocol maxes out at some point, and the latencies go through that roof. That's the capacity of that protocol. Notice the logarithmic x-axis on the graphs. For watchmaker, the peak throughput at the saturation point is 100x higher than for the other protocols. The quasi-synchronous model enables watchmaker to leverage clock sync for ordering and the bounded packet loss assumption for agreement. Next, we'll have a closer look at the latencies. One of the key problems with existing SMR protocols is that the latency can vary quite a bit. This is because of the asynchronous uncoordinated network and all the messages that have to go back and forth among replicas for complex ad hoc coordination. Here, I'm showing the CDF of the latencies for watchmaker's main competitor, Neja. You'll see here in this graph that Neja had a really long latency tail. Sometimes it takes hundreds of milliseconds until we get a response. But with watchmaker, the latency is much shorter in terms of the tail, just a few hundred microseconds, or roughly 1000x less than with Neja. That's because we carefully schedule a network for watchmaker, so there really isn't any queuing in the quasi-synchronous replica network. To summarize, distributed systems often assume that the underlying system is asynchronous. This assumption is extremely conservative, especially for a single-tenant data center. In our paper, we propose an alternative model that captures more of what modern hardware can actually do, and we call this model the quasi-synchronous model. As a case study, we presented Watchmaker, a quasi-synchronous protocol for state machine replication. The benefits of Watchmaker relative to asynchronous SMR protocols are quite substantial. In particular, we get 100x high throughput, 1000x lower tail latencies, and last but not least, we have to buy about 50% fewer servers. That's all I have for today. Thank you so much.